Hi everyone, welcome once again to our discussion for today. We'll continue on the partial derivatives, but this time we have partial derivatives of functions with more than two variables. Actually, we had discussed this already in separate discussions, especially in the big blue button at U step. But this time we are going to make a little review on this part before we go to the higher derivatives. So for a function of more than two variables, like for this one, we have function of x, y, z. So a function of three variables, there are three partial derivatives. Namely, we have these notations: f sub x of x, y, z, f sub y of x, y, z, and f sub z of x, y, z. So these are the three notations for the three partial derivatives. The partial derivatives of f sub x is calculated by holding y and z constant and differentiating with respect to x. For this one, partial derivative of the given function with respect to y, so the value of x and z are held constant, and for f sub z, the variables x and y are held constant. All right. If a dependent variable given by this expression w equal to function of x, y, z is used, then the three partial derivatives of the given function f can be denoted by this: partial derivative w with respect to x, partial derivative of w with respect to y, and partial derivative of w with respect to z. Okay, for example, if you're given, say, if f of x, y, z equal to x cubed y squared z to the fourth plus 2xy plus z, then we have the following partial derivatives. So the first one, the partial derivative of the given function with respect to x. So when with respect to x, so the first one, we need to hold y and z as constant. All right, so we hold y and z as constants. All right. So for the result, so if y and z constant, so therefore for the first term, so y and z constant, so y squared z squared constant, so we just take the derivative of x cubed. Okay, just take the derivative of x cubed. So using the power rule, so derivative of x cubed, that is 3x squared, right? Then multiplied with y squared and y to the fourth. So that's why we have here 3x squared y squared z to the fourth. Then for the second term, so y is constant, 2 is constant, so we just take the derivative of x. So derivative of x with respect to x equal to 1, 1 times 2 times y, so that's why we have here 2y. All right, then z, since z is held constant, so derivative of constant is equal to 0. So that's why for the first derivative, so we have this. All right, now for the second one, partial derivative of the given function with respect to y. So for this part, we need to hold x and z. So this time, x and z are held constant. Okay, so if x and z are constant, then what will happen here? So x and z constant, x and z constant. So we have to take the derivative for the first term, only this one. So again, power rule. So derivative of y squared is 2y. 2y times x cubed and z to the fourth. So that's why we have 2x cubed y z to the fourth. We just rearrange. All right. And then for this one, x constant, 2 is constant, so we'll just take the derivative of y. So derivative of y with respect to y is 1, 1 times 2x. So that's why we have here 2x. Okay, so this is for this part. Now the third one. So for the third one, partial derivative of the given function with respect to z. So if with respect to z, then we need to uh, hold x and y as constant. So x and y constant. Okay, so if x and y are constant, so therefore, so x cubed y squared constant. So we'll just take the derivative of z to the fourth using power rule. So derivative of z to the fourth, that is 4z cubed. So 4z cubed multiplied by x cubed y squared. So that's why we have here 4x cubed y squared z cubed. All right. So x and y constant. So x and y constant. So therefore, derivative of this is 0, right? Because 2 is constant, x is constant, y is constant. So the whole thing here, the whole product here is constant. So derivative of a constant is equal to 0. So therefore, we have for the third term, derivative of z with respect to z is equal to 1. So that's why we have here 1. Okay, so these are the three partial derivatives. So hope you were able to follow, class. Okay, so this is for example number 10. Another example here. By the way, if you are given, say, the value of x, y, and z, for example, you're given the value of x, y, and z. So assuming this is given, this is also given, and you are asked to find for, say, for example, f sub z. So what's your values? For example, you are given the values of x, y, and z. So you have f sub z, then you have something here inside the parentheses, then you're asked to evaluate. Okay, so like this one here. So for example, you're given the value of x negative 1, y equal to 1, z equal to 2. Then therefore, the value of the derivative at this point is equal to something like this. So use whatever is the subscript here. So that will tell us which of these following derivatives that we're going to use. So in this case, we're asked to solve for f sub z. Okay, and substituting the values, we got negative 31 here. All right, so for the next example, we're given a function of p, theta, and phi equal to uh, this symbol, p squared. So how do you call this symbol? Sigma, then times cosine phi sine theta. All right, so this is the given this function of three variables. Okay, so this symbol, then theta, phi, I forget the name of the symbol. Okay, equal to this rho. Okay, I remember now. This is rho. So f function of these three variables, rho, theta, and phi, equal to rho squared cosine, no, rho. I think this is the spelling. Cosine phi sine theta. So we have here phi and theta. All right. So taking the partial derivative of each of these variables, so we have here the result. So when you take the partial derivative with respect to this one, okay, so with respect to this, so it means you have to hold these two variables. as constant. So we have to take or consider theta and phi as constant. All right, and we get this result, and then apply the formula for derivative of sine, the derivative of, but anyway, this one is constant, so cosine of constant is constant, sine of constant is constant, so we take only the derivative of this. All right, so derivative of this using the power rule, so we have 2p. All right, then for this one, so next we take the derivative with respect to theta, so it means that we have rho and phi considered as constant. All right, so rho constant, then we have phi constant, so we'll take only the derivative of this. So derivative of cosine is minus, right? Sorry, derivative with respect, sorry class, theta. Yes, this is with respect to theta, so phi. All right, so rho and phi constant, so we'll just take the derivative of this sine, no? Derivative of sine. So what is derivative of sine? That is cosine. So that is why we have rho squared cosine phi, they're constant. We'll just take the derivative of sine. Derivative of sine is cosine. All right. So this is the result. Then finally we have the derivative of this function. So this time with respect to phi. So if with respect to phi, then we have rho and theta as constant. All right. So rho is constant, theta is constant. So we'll take the derivative only of the, sorry here. Always look at the given function. Okay, so look at here. We have uh, rho is constant, theta is constant. All right, so we'll just take the derivative of this. So which is derivative of cosine is minus sine. All right, so this is minus sine. We'll just put the negative here, okay, to rearrange. So derivative of cosine is negative sine. So we have sine phi, sine theta. All right, so this is the result. Okay, so this is it. And in general, if the function is a function of, say, 2, 3, or 4 or more variables, so if we are given a function that is a function of n variables, so there are n partial derivatives of f. So it means if you have 5 variables, so you have 5 partial derivatives. If you have 10 variables, so you have 10 partial derivatives, and so on and so forth. So in general, if the function is a function of n variables, so there are n partial derivatives of f, each of which is obtained by holding n minus 1 of the variables as fixed or constant and differentiating the function f with respect to the remaining variable. So if w is a function of v1, v2, and so on and so forth until vn, then the partial derivatives are denoted by this. So partial derivative of w with respect to v1, a partial derivative of w with respect to v2, and so on and so forth until we have partial derivative of w with respect to vn. Okay, so that's all for this part. Thank you very much, and see you again in our last topic for this partial differentiation, and that is uh, higher order partial derivatives. Thank you, and see you again in the next video. Bye.